So now if you solve this equation, we will get 34.81 around kilogram. So the kilogram of copper that is taken is 34.81 kg. Again, let's coming back to the problem. We will just repeat whatever we had done. So this is like mass of copper that we need to determine. Okay, we have a calorimeter setup wherein it is completely filled with a block of ice at 0 degrees Celsius, and it's 1 kilogram of ice at 0 degrees Celsius, which is mentioned here. And the copper that is available is at 25 degrees Celsius. So the copper is lying in the center of the calorimeter at 25 degrees Celsius, which is surrounded by ice at 0 degrees Celsius, and the ice is 1 kilogram. So now we need to find the mass of copper, and we know that final stage is ice is completely converting into water at 0 degrees Celsius, and the final state is both water and the aluminum are becoming 0 degrees Celsius. This is the thermal equilibrium state, and they are asking us to find the mass of copper. So how we are going to proceed is we are going to consider zeroth law of thermodynamics, which is nothing but the principle of calorimetry, which is nothing but law of conservation of energy, which states that whatever the heat is being rejected by someone is going to be absorbed by someone. So that heat rejected is by copper. I'm interchangingly using copper and aluminum. You can consider this as copper. So the heat rejected by copper is obviously gained by the surrounding ice block completely, and no heat is lost. That is the assumption. So equating the heat lost by copper equal to heat gained by the ice. Heat gained by ice is by virtue of latent heat of fusion, and it's not involving any temperature. So mass of ice is, we all know that it's 1 kilogram into 336 into 10 power 3 is the latent heat of ice. So I am dividing that by, to find the mass of copper, I am dividing that by specific heat capacity of copper, which is nothing but 0.386 into 10 power 3 joules per kilogram Kelvin, into temperature difference, that temperature drop that the copper has experienced, which is nothing but the 25 Kelvin or 25 degrees Celsius difference. So by equating this answer, I am getting 34.8 kgs. So this is how we derive at the mass of copper, and this is one of the applications or uses of calorimeter. Now the next question we will just extend to the 2011 question. What will happen if you add impurity to boiling point? So now let's take water. So this is also the same context. You cannot simply generalize this question and answer to this question. This will depend on the material that you are taking and whatever impurities you are adding. So in this case, we will just go with water or water vapor to answer this question. Because most of your questions will be related to water and water vapor only. You will not be given any other substance, so you need not worry. So now you know that water will start to boil at 100 degrees Celsius without any impurities if it's a pure water. So this is fine. But what will happen if I am giving to my friend with the water containing salt or saline water? So the boiling point is going to change to something like 110 degrees Celsius. The boiling point is going to increase. Earlier, if you remember, the melting point, when you add impurities, it's going to reduce. And the boiling point, whenever you are going to add some impurities, it's going to increase. Now the water is having a boiling point of 110 degrees Celsius. So the answer is straightforward. Like when you add impurities to water, the boiling point of water is going to increase. And this is specific to water. We don't know about any other material and whatever other impurities you are going to add. This is plus salt. It again depends on whatever material you are considering and whatever impurities you are adding. This applies to melting point as well. And for this case, if you add impurities like salt to water, it's going to increase its boiling point. But what is the application of this? So whenever you boil a water at 110 degrees Celsius, you are having an advantage of storing more heat at 110 degrees Celsius without the water getting converted into steam. So whenever you are cooking in a vessel, for example, this doesn't apply for a pressure cooker, I will come to that later. You are having a rice. The rice is getting boiled in normal pot. So let's assume if your water is boiling at 100 degrees Celsius, right? Whenever you are giving heat at 100 degrees Celsius, the water starts to vaporize. Whatever water is available in the pot, only that will cook this rice. So you need more water and you need more gas to cook. But the same way, if you are adding this salted water, okay, the same rice, same quantity of water, but it is salted water. This will boil only at 110 degrees Celsius. So what will happen is, only after reaching 100 degrees Celsius, the water will start to vaporize. So till then you will have that water available at 110 degrees Celsius and it will cook the rice. So the time in which the rice is going to be cooked will be higher, because here it is cooking at 100 degrees Celsius, here it is cooking at 110 degrees Celsius. You can simply see it is cooking at higher temperature, which will be more efficient compared to 100 degrees Celsius cooking. In 2009, we have one more question. So, what is meant by principle of calorimetry? See, principle of calorimetry works on the principle of law of conservation of energy. Okay, so which means energy of the universe is constant, and you will have a second derivative, change in energy of the system is equal to change in energy of the surroundings. Which means, for example, if a ice is gaining heat, which means its thermal energy is increasing, it is gaining heat, and the surrounding is giving the heat. So which means whatever the thermal energy that is gained by the ice is equal to whatever the thermal energy that is given out by the atmosphere. So this is law of conservation of energy, and calorimetry also works on the same principle. It works on law of conservation of energy. What does that mean again? Energy lost by a system, or okay, we will go with the energy gained by the system. Energy gained by the system will always be equal to energy lost by the surroundings. If you put the other way, energy lost by the system will always be equal to energy gained by the surroundings. So whatever lost here should be gained by someone. So that is the core principle of calorimetry. Then there is a question. After a heavy hailstorm means it will be consisting of ice particles. Okay. After a heavy hailstorm, the weather will be too cold. Okay. After a heavy hailstorm, your weather will be too cold. What is the reason? Because this is very simple reason. This is ice, nothing but the hail. Okay. When the hailstorm occurs, when it falls to the ground, okay, for each kg, it will absorb 336 kilojoules of heat. This ice at 1 kilogram can take in heat of 336 kilojoules of heat. This is nothing but the latent heat of ice. Latent heat of fusion of ice. So what happens is, 1 kilogram of ice takes in this much amount of heat from the surroundings and get converted into water. Assume that hailstorm, how many kilograms of ice it produces, and it multiplied by this 336 kilojoule, that much amount of heat it is taking from the atmosphere. So obviously when the heat is rejected from atmosphere, atmospheric temperature will cool down. This is similar to the farmer's case that we saw. So which means, like, obviously our temperature of the atmosphere is going to fall and the weather is going to be cooler. This is because each kilogram of ice is going to take in 336 kilojoule of heat from the atmosphere. Very simple reason, latent heat of fusion of ice. The same here, the next question is the previously we have discussed already. Because what is happening is, when ice melts, or any substance in solid state, when it melts to liquid state of the same substance, mass is same mass, it will be produced after melting. So fusion is happening. Okay, and you are giving some heat. So though the temperature is same T, here also same T. So mass is same, temperature is same. So what is happening with this heat? Something is making this to change phase. So something is happening, but what is happening is, it's not causing any kinetic energy increase or kinetic energy decrease in the molecules. Rather, as we already discussed, it is just increasing the intermolecular spaces between the molecules present in the body, causing it to change phase. So it is just weakening the intermolecular bond between two or more molecules present in the body, making it to convert from solid phase to liquid phase. So that is the question that is asked in 2010. And there is one more question asked in 2010 the same year. This is also an interesting one. The same thing which we already discussed. So, okay. What is the use of high specific heat capacity substance? This is the same thing that we discussed some time back. High specific heat. So high specific heat capacity are used in defrosting agents, particularly farm fields, because water is cheaper. I mean, when you consider high specific heat, the first thing comes into our mind is water, because it is easily available, cheaper, and is available in large quantity. So high specific heat capacity, why it is defrosting farm field? Sorry, it's not fielding, farm field. So a farmer will sprinkle a lot of water during a frost season to prevent his crop from frosting the next day, because water will absorb 4.2 kilojoules of, sorry, it will not absorb, water will release 4.2 kilojoules of heat, and it reduces its temperature by 1 Kelvin for 1 kilogram. So which means water for 1 kilogram, it is able to give out heat of 4.2 kilojoules. So it will at least give some heat to the plants by reducing its temperature in such a way that it will not allow the plants to frost. So it will not like save the plants completely, but at least it will reduce the time in which the frosting of the plants happen. So it will be available in defrosting applications. Second thing is, in countries like US or any other countries where the temperature reaches in minus, say for example, they are going for a party, and you will probably see that all the cold drinks that they have, right, they will be put in water. Not in countries like India, they will put it in ice, but in their countries you can see that they will put it in water. Because the primary difference between they are putting it in ice in our country and putting the water in their country is different. I will first talk about why they are putting the cold drink in water, and then I will come to Indian country. So here, this cold drink might be at a drinkable temperature 12 degrees Celsius. I don't know why it is not writing. This will be at 12 degrees Celsius, a drinkable, or let's say 16 degrees Celsius, something around a drinkable temperature. Okay, so now if you keep it like this, because the atmosphere in their conditions will be like frosting temperature, like minus 30 degrees, minus 12 degrees Celsius, minus 13 degrees Celsius, something around that temperature it will be prevailing in their atmosphere. But the cold drink is at 16 degrees Celsius. So obviously, during their discussion, if they are talking and then having a chit chat, if they keep it as it is, minus 12 degrees Celsius means this 16 degrees Celsius will lose heat to this surroundings, and it will slowly start to solidify. The drink will not be a drink, it becomes solid soon. So to prevent that, what they will do is they will put it in water. Water will also be at atmospheric temperature, minus 12 degrees Celsius, close to. But again, let's assume that this is having like, they would have heated the water to some degree Celsius, say 5 degrees Celsius, and they will put it in here. Still, what will happen is the cold drink, which is at 12 degrees Celsius, will be losing heat to this 5 degrees Celsius water, but not at the rate it is releasing heat to the minus 12 degrees Celsius. In a nutshell, this soft drink which is immersed in water will not frost, because the 5 degrees Celsius water, or whichever degree Celsius the water is prevailing, will give out some heat to this body, while this water is giving out its heat to surroundings. This is not water, this is drink. So whenever a high specific heat capacity substance is used and soft drink is immersed in it compared to a very cold surroundings, it will prevent the frosting of that drink by supplying the heat present in water to that drink. So again, like 1 kilogram of water, it can produce to 4.2 kilojoules of heat to this soft drink, and it increases it loses its temperature by 1 Kelvin. So obviously they will use water just to prevent the frosting of the cold drink, so that it will still be available in liquid state, so that anybody can consume while chit-chatting for long hours. The same case when it comes to India. the outside temperature will be 38 or 40 degrees Celsius. So obviously if the drink is 16 degrees Celsius, it is going to lose heat, and this 16 is going to increase till 38 degrees Celsius. So you don't want to drink something which is at 38 degrees Celsius, otherwise it's not cold drink. So what they will do is they will put ice. So you can know the primary difference now. The outside temperature is less than less than the temperature of the soft drink. So they have used water to put it in the same liquid state itself in foreign countries. But in India, the outside temperature is too high compared to a soft drink. So to maintain the soft drink at its temperature, we need to remove heat continuously from the soft drink wherein we are putting ice. So this is the primary differences that we need to understand. So now to answer this question, high specific heat capacity of water can be used in defrosting application. One of the applications is farmers will sprinkle water on his crops during night time to prevent the frosting of its crop, or to prolong the frosting of his crops to prevent to have more yield or good yield. And the next thing is, in foreign countries wherein the temperature goes in minus, they will use a bucket of water and wherein they will put the soft drinks into it so as to maintain the liquid state of the drinkable soft drink. Otherwise it will frost and become solid state soft drink. So this is the high specific heat capacity usage. Now just we will extend this to low specific heat capacity as well. So which all applications will use low specific heat capacity? Mostly it will be by heat exchangers and cooking. Cooking we just saw a few times back. Why cooking needs low specific heat capacity substance is that whatever the heat that you are giving should be totally available for the cooking process. For example, if you are cooking noodles, if you are cooking rice, the heat that you are giving should always be available, or should be maximum be available for cooking the actual thing, cooking the actual product, cooking the rice or cooking chapati, whatever. But if it is having high specific heat capacity, the heat that you are the heat that you are giving will be utilized by the utensil itself maximum, and only like very small amount will be used for actual cooking of the product. What will happen in this case is you will burn up a lot of gas which is unnecessary, and it will give you more bill on your gas. So we always use low specific heat capacity, and there is one more advantage of using low specific heat capacity on cooking is that the cooking will be faster. The utensil will attain higher temperature in a shorter span of time. So that's why cooking always prefer low specific heat capacity substance. Heat exchanger, we just saw a similar example wherein our fridge will be having a low specific heat capacity copper coils, blackened. The black color is this black color is just for a different reason. We will not touch it for now. And why copper is being used is that because copper is having low specific heat capacity, it will not absorb much of the heat to increase its temperature. To maintain a higher temperature gradient, for example, if your heat is Q and you are using copper here, it will be at a higher temperature compared to the same Q energy given to some other material. Let's assume this is given to water, assuming that this can be done in solid state. Water can be coiled. So water will be at a lower temperature though it is given at Q. Whenever you are having a higher temperature for the same amount of heat, then the heat transfer that you can do to the surroundings will be higher. So in a nutshell, what will happen is, for the same quantity of heat available in a material, if you want to lose that heat, you need to have a low specific heat capacity of that material, because that is when you will have, for the same amount of heat, you will have more temperature. More the temperature gradient with respect to surroundings. So the T minus T surroundings, T of system minus, that is T of copper minus T of surroundings, will be higher. Then only you will maximize the heat transfer to the surroundings so that your fridge will cool faster. Okay, so these are the two applications that you can use for low specific heat capacity materials. This is very important that you will be asked very frequently in your ICSE board exam.